Whenever you want to start, I'm ready.
Okay, good. So welcome to everyone who is listening in. So welcome to a new day of talks. Today is going to be exciting. So we start with a talk on quantum PCPs and the randomization. And then later we have 3 talks about MIP star. And I think that there's a little theme that is going on, because you can look out for a lot of PCPs, probabilistic checkable proofs, and also sort of transformations that preserve the gap or amplify the gap. In Alex's talk, we'll see them in the context of local Hamiltonians and later in the context of non-local games. So, okay, without further ado, let me introduce the speaker. We have Alex Grilo from CWI and QuSoft in Amsterdam. And take it away.
So thank you everyone for joining in. Thanks for the organizers for setting up this wonderful workshop. And okay, I'm very proud to be here. This is my first after dinner talk. So, and I'll explain my joint work with Dorita Haranov on this unexpected connection between quantum PCPs and derandomization. And these are 2 very important open problems in complexity theory. And I'll try to explain from the beginning, from scratch, what they are. So to start, we know that there are a lot of settings where randomness helps a lot. So as we saw, for instance, yesterday in Andrea's talk, for instance, if you have no local games, the referee must pick random questions to send to the peers. But we know that, at least we expect that randomness won't help in every case. So for instance, we expect that for polynomial time computation, random coins do not help. And you can see this because, for instance, if pseudo-random number generators exist, then every randomized algorithm can be turned into a deterministic one. And the existence of pseudo-random number generators is supported for widely believed conjectures in complexity theory. So it's a bit embarrassing because we know that it should be true, but it has been an open problem for a very long time. And just to, I don't know who's in the audience, but for those who have never seen about derandomization, let me give an example of why it's hard to derandomize problems, or derandomize algorithms, sorry. And one example is in this problem called the polynomial identity testing. And in this problem, the input is a polynomial P on, let's say, on some field, finite field of Q. And the input is n fq to the n, and then it outputs some element in fq. And this polynomial has degree at most p. And you want to know if for every possible input of this polynomial, it evaluates to 0. And you can think that here, this polynomial is given in an implicit way. So for instance, you have a circuit that computes this polynomial. And there is a very simple randomized algorithm that does the following. So you just pick the input uniformly at random and try to evaluate this polynomial to 0. And if indeed this polynomial is 0 for every possible input, it will be 0 for this randomly chosen one. But what we can show is the polynomial is at 0. Then if you pick one of such inputs uniformly at random, then with high probability, you won't hit a 0. So this simple randomized algorithm somehow allows us to find such a witness that this polynomial is not 0, and we don't know how to do it deterministically. We don't know how to search for these witnesses or for these inputs without having random coins. And in this talk, I'm interested in this in the derandomization scenario when you're talking about verification of proofs. And for that, we start with the complexity class NP that you might know, but let me recall it. So we say that a problem is in NP. If there is a deterministic polynomial time verification algorithm D, and receives X. That's an instance that you want to know if it's a positive instance or a negative instance of this NP problem. And Y, which is called a certificate or a witness. And this deterministic algorithm on input X and Y decides to accept or reject. And the language in NP, if for every positive instance, there exists some witness that makes this deterministic algorithm to accept. And for no instances, no matter which witness is given to the deterministic algorithm, it should reject. And NP is a central object in complexity theory and even in computer science. So it has been extended in different contexts. And one of such contexts is in randomized computation. And then we have the randomized version of NP that's called MA, and it stands for Merlin-Arthur. And here it's almost the same thing as NP, but now this verification algorithm is a polynomial time random computation. Polynomial time random computation, yeah. And that's given, again, one instance that you want to know if it's positive or negative, and a witness that should be verified by this randomized algorithm. And here we want that for yes instances, that there exists some witness that will make this randomized computation accept with high probability, whereas for no instances, no matter what witness is given, this randomized algorithm should reject with high probability. And what I think is that we can also we can improve a little bit this first line for positive instances. We can assume without loss of generality that it is one, like there's a theorem proving that. And as I said before, even in the NP versus MA case, we believe these two complexity classes to be the same. So randomized computation wouldn't help even for verifying proofs. But again, this problem has been open for a long time. And in one line, our result in this work is showing that some sort of quantum PCP conjecture is equivalent to the randomization of MA. And I'll wait 5 seconds if there is any question on the definition of NP and MA.
By the way, if you have questions, you can, as usual, write them in the Q&A, or you can raise your hand and I'll unmute you.
Okay, if there are no questions, so I'll explain a bit better what our result is. And for that, I have to make a detour in Hamiltonian complexity. So we know that from quantum mechanics that the evolution of physical systems are described by Hamiltonians. And one very important problem in condensed matter physics is finding what's the configuration of the particles that minimizes the energy of such Hamiltonian. And this configuration of particles is called the ground state of that Hamiltonian. And in nature, you have particles that are far apart. They tend not to interact. So usually these global Hamiltonians, they can be decomposed as a sum of smaller terms. And our goal here is trying to study this problem through the lens of theoretical computer science. And for that, let me define this problem more formally. So we assume that the input of we have that the input of such a problem. Sorry? Okay, sorry, I heard something. No. So we have that the input of such problem is m local Hamiltonians, and I say they are local because each of them act on at most k out of n qubit system. And for those who are not so familiar with Hamiltonians, so meaning that they are k local, it means that every hi is a tensor product of identity, and this is a term hi tilde that acts on at most k qubits. And a Hamiltonian is nothing more than a Hermitian matrix, so we can think as just some matrix that is self-adjoint. And also, we assume that each one of these terms has bounded norm. Let's say that the norm is bounded by 1. And given these m local terms, we consider then the global Hamiltonian, Hamiltonian H, as the sum of these local terms. And our goal here is distinguishing two cases. The first one, when there is some state that has low energy, according to this Hamiltonian, so it's below some threshold alpha m, or decide if every state has high energy. So for every state, the energy of the Hamiltonian is above some threshold beta m. And for those not so familiar with quantum, we're just talking about what the smallest eigenvalue of this emission matrix. And in complexity theory, okay, given a problem, we want to understand how hard this problem is. And in order to explain the hardness of this local Hamiltonian problem, I'll go back to the complexity class, and I have to define the quantum version of MA. So this is called the complexity class QMA. And in this complexity class, it changes because now the verification algorithm is a quantum algorithm. It receives, as before, the instance of the problem, but now it also receives a quantum proof that will allow this quantum verification algorithm to accept or reject. And now we want that for all positive instances, there is a quantum state that makes this quantum verification algorithm accept with high probability. And for no instances, we have that all quantum states makes this quantum verification algorithm reject with high probability. And here, differently from the probability case, we don't know if it's possible to assume without loss of generality that for the yes case, we can make it 1. I'll stop for 3 seconds if there's any questions on QMA. Okay, so back to the local Hamiltonian problem. So as I said, the input is...
Alex, sorry, we just got a question in the chat. The question is, how should we think of K and M with respect to N? What is the intersecting range of parameters?
So K is a constant. Let's say K is 5. And what's the other parameter?
N. The other parameter is N.
Oh, N. Oh, sorry. So N. So for the local Hamiltonian problem, N is the size of your system. So you fix N, and then the number of terms is polynomial in N. So it's a bit different from what we have usually in computer science. N is the number of qubits. So, but K is a constant. And let's say it's 5 here. And and again, okay, what you want is to decide if the energy, that there is a state with low energy, or all the states have high energy according to the Hamiltonian. And Kitaev showed in '99 that if you pick beta and alpha to be at least an inverse polynomial, so this problem is actually QMA complete. Meaning first that it is in QMA, and the QMA verification for the local Hamiltonian problem, like the prover just gives this supposed to be low energy state to the verifier, and the verification algorithm just checks if the energy is small or large. And what Kitaev also showed is that this problem is QMA hard, showing what we call the quantum Cook-Levin theorem, and reduce every problem, generic problem in QMA to an instance of the local Hamiltonian problem. And now that you have that this problem is QMA complete, we can think, okay, for which range of parameters does it remain QMA complete? Or for which range of parameters it becomes easy? And for one very important set of parameters is when beta minus alpha is a constant. So here we have a much bigger gap between the yes and no instances. So it should be a much easier problem. But the quantum PCP conjecture states that even with this very large gap, this problem remains QMA hard. Any question? So given the importance and applications of local Hamiltonians in quantum computing, people also started studying how hard is this problem is when you don't consider like the arbitrary local Hamiltonians, but restricted families of local Hamiltonians. And one family that was considered for the strict restricted local Hamiltonians is what's called stochastic Hamiltonians. And the definition is a bit counterintuitive, but it is just defined by a Hamiltonian is called stochastic if every HI has non-positive off-diagonal elements. So the diagonal could be anything, but off-diagonal is either 0 or a negative value. And the first thing that you notice is that this definition is base-dependent, but we assume that we're given this Hamiltonian in a basis where such a phenomenon occurs. And why people have considered this is because these models the first machines that were developed by the way. As I said, this definition is a bit counterintuitive, but it has very nice consequences. So instead of considering the Hamiltonian HI, we could instead consider the projector onto its ground space. And the stochasticity of Hamiltonian gives us very nice properties for this projector. In particular, it allows us to write it as a sum over orthogonal rank 1 projectors. Okay, since it's a projector, it can always be like this. But each one of these rank 1 projectors is spanned by on a subspace is spanned by a state with only real non-negative amplitudes. So here, PI is a sum over projections over positive states or non-negative states. Sorry. And this implies that this Hamiltonian HH, it must have some ground state that only contains non-negative amplitudes. And that's why they coined the term stochastic, because somehow you can see these amplitudes, these non-negative amplitudes, as a probability distribution. So it is something between stochastic Hamiltonians and fully quantum ones. Any question about the definition of stochastic Hamiltonians? So in this work, we restrict even more this family of stochastic Hamiltonians, and we consider what we call uniform stochastic Hamiltonians. And in this family of Hamiltonians, we consider the only states in this rank 1 projector that only contain the same amplitude. So we can just consider sets of strings, and the state is just a uniform superposition over the set of strings. And then this PI is a sum over what we call the subset states. And this has another nice consequence in the ground state. It's now we can prove that there is a ground state that is just the uniform superposition over the strings in some set S. Okay, and for the purpose of this talk, these are the types of Hamiltonians that we'll be considering. So having defined these stochastic Hamiltonians, we can go back to the local Hamiltonian problem and study what happens to the hardness of the problem when you know that the input are stochastic Hamiltonians. When the input that's given to you, they are stochastic. And here we also want to solve a bit easier problem. We want to decide if this Hamiltonian has some state with energy 0. And sometimes we call it that this Hamiltonian is frustration free in this case. Or if the ground energy of this Hamiltonian, so the smallest eigenvalue of H, is at least some beta m for some parameter beta. And again, we want to understand how hard is this problem. So then in 2008, Bravo and Terhall, they showed that for some inverse polynomial beta, this problem is MA complete. So this is very surprising for 2 reasons. So first, it is the first MA complete problem. So it has been defined for more than 30 years. And this is the first natural complete problem for this complexity class. And second, being the first one, it comes from quantum computation. So I think it's very surprising, this connection between quantum and randomized computation. And here, the MA hardness of this problem comes more or less for free from the result of Kitaev, and the really novelty here comes from proving that this problem is in MA. In particular, that you can decide between these 2 cases with only classical algorithms that toss coins.
Alex, there's a question from the chat. So
yes?
is there any restriction on S? I guess this was on the or S can be any subset. I guess this was from the previous slide.
Oh, here, no. No, I'm just saying that, so here S, okay, what I claim here is that there is a ground state such that there exists an S, such the ground state is the uniform superposition over the strings in S. That's just a claim that there is such an S, such that this works.
Mm-hmm.
Okay?
Yeah.
So, as I was saying, so for an inverse polynomial beta, Bredariol showed that this problem is complete. And our result here is showing that if beta is actually a constant, it could be any constant, then this problem is actually an NP. So if you have a promise that this gap between yes and no is much larger, then we don't need coins to solve the problem. We can solve it deterministically, given some proof, given some initial, some classical proof. And for the rest of this talk, I'll explain a bit more this connection between Hamiltonian complexity and randomization. And then I'll go into a bit more technical details between like how to show that stochastic local Hamiltonians are in MA. And finally, give a proof sketch of my result with Dorit. And finally, I'll finish with some open problems. So let me put our result and the result by Bredariol side by side. So they show that deciding if the uniform stochastic local Hamiltonian has ground energy 0 or inverse polynomial is MA complete. And the only difference to our result is that now the gap is between 0 and constant, and then we're allowed to show that it's in NP. So let's suppose that there exists some deterministic polynomial time map that maps stochastic Hamiltonians to stochastic Hamiltonians with the following properties. So the output is a uniform stochastic Hamiltonian, and when k is a constant, and also a parameter that I didn't define, the degree is also constant. So you know that the output is nicely behaved.
Alex, sorry to interrupt. We have a question in the chat. So Dominic asks, what does uniform mean in those theorems?
Oh, uniform is what I said, that I assume that the terms are these Tij's. Like these rank 1 projectors, they are on subset states instead of any arbitrary non-negative state. Is this fine?
Mm-hmm.
Okay. So as I said, I want the output of this map phi to be a nice stochastic Hamiltonian. And we want that if the input Hamiltonian is a stochastic Hamiltonian with ground energy 0, the output has also ground energy 0. Okay, so if the smallest eigenvalue of H is 0, the smallest eigenvalue of H prime is also 0. And if H has ground energy inverse polynomial for some fixed polynomial, then we want that the ground energy of this H prime, that's the output of this map, is constant. And this map in complexity theory is called a gap amplification procedure. So it's amplifying the gap, the promise gap from H, and now it's bigger in this H prime. So you have that if this gap amplification procedure exists, then MA equals NP. And let me describe why this follows. So we can start with a problem in MA. And by Bredariol, we can reduce this problem in MA to a stochastic local Hamiltonian instance where the promise gap is inverse polynomial. Then, from the assumption of this map phi, we can reduce this instance to an instance of the stochastic local Hamiltonian problem, where now the promise gap is a constant. But what we show in our result is that for every constant, this can be solved in NP. So if such a map exists that we don't, this is the only missing part, we have that every problem in MA is in NP. and it seems too good to, this map seems too good to be true. And why does it exist? So we know that for classical Hamiltonians, they exist, and this is exactly the PCP theorem. It shows that we can map, we can have a gap amplification procedure for classical Hamiltonians. The quantum PCP conjecture, then it conjectures that such a map exists for general Hamiltonians. So this map that we're considering here, that I just defined, it can be seen just as stochastic PCP conjecture. So we want that this map that does gap amplification exists only for stochastic Hamiltonians. And as I said, our corollary of our result then is showing that this stochastic PCP conjecture is equivalent of derandomized MA. And one could see this in two ways. So one, you can see that, okay, we're advancing in the MA versus NP problem. So we have a new way of attacking this problem. Maybe you can do it through quantum arguments. So showing that this stochastic PCP conjecture exists, or that's true. But a different way of seeing it is that actually proving quantum PCPs should be very hard. Because in particular, proving some sorts of quantum PCPs would be also solving the randomization. And we know that's a very, very hard question.
Can I have a question here? So,
yes.
Like you had some like extra conditions on this map. So like how natural are those? So it seems that like some specific version of stochastic PCP is equivalent to this MA equals MP problem, but one could maybe imagine that somehow it doesn't preserve perfect completeness or something.
So about completeness, I'll say something more about the end, but it's true that, okay, it's not that any gap amplification map would imply MA equals NP. It's just a gap amplification procedure with these properties. But, okay, one thing that makes us hope is because the classical gap amplification procedure has these properties, for instance. So I think, yeah, I'll say in the open problems, the way of solving this is showing that the stochastic local Hamiltonian problem is in NP for a broader set of parameters. This would make this reduction more flexible.
Sorry, another question. Isn't it plausible that one could prove the general quantum PCP conjecture, but without proving the stochastic PCP conjecture?
Yes, it can. So yeah, in this way, you can see this is somewhat as a barrier. So if you want, you can solve quantum PCP without solving the randomization by either putting signs or losing perfect completeness. So there are ways of solving quantum PCPs, but you can see this as a barrier of proving them. So without solving very hard problems. Okay.
Thanks.
So let me continue, and then now I want to talk a bit how Bravo and how they show that these stochastic Hamiltonians, they can be solved in MA. And for that, they define some implicit graph. And so if the Hamiltonian acts on an n-qubit system, then the vertices of this graph are just all the possible n-bit strings. So that's why it's implicit, because it's an exponential size graph. And we connect to vertices in this graph if they belong to the same projector of the local Hamiltonian. So let me explain this by example. It will be more clear, I think. So imagine that you have a 3-qubit system, and you have 3 local terms. And here I'll define just the projector onto the ground space of these local terms. The term acting on qubit 1 and 2. This projector is spanned by the states psi 0, or psi 0 is 0, 1 plus 1, 0, and phi 0, where phi 0 is 0, 0 plus 1, 1. And tensor identity on the 3rd qubit. And the same thing for P3, where now we will have an implicit tensor identity on the 1st qubit. And finally, the projector of this Hamiltonian on the 1st and 3rd qubits is spanned by the states 0, 0, 0, 1, and 1, 0. And since here we have a 3-qubit system, because our graph will have all the possible 3-bit strings. And let's say, for instance, let's look at the node 0, 0, 0. For instance, if you look to the projection P12, we see that 0, 0 is a neighbor of 1, 1. So we keep the third bit, but we change the substring 0, the initial substring 0, 0 by 1, 1, and we connect these two vertices in the graph. The same thing happens for P23. We still have that 0, 0 is in the same ground state of 1, 1. So we connect the vertices where we maintain the first qubit, or sorry, the first bit, but we change the last 2 bits from 0, 0 to 1, 1. And finally, P13, 0, 0 does not have neighbors. So we don't need to add any extra edge because of P13. Having defined this graph, Bredariol and Hall, they also define a notion called bad strings. And a string X is said to be bad if there is some Hamiltonian such that X is not in the ground state of that Hamiltonian. So in particular, if you look to the string 101 and 111, you see that the 1, is not in P13. So the strings 101 and 111, they must be bad because they never project into it. So having defined this implicit graph, so Bredariol and Hall, they define what the May verification procedure. And here, in this May verification procedure, it assumes that the prover or someone gives as a proof of that the Hamiltonian insertion has energy 0, an initial string x0 that's supposed to be in the ground state of this Hamiltonian. And the verification algorithm just performs a random walk on that implicit graph for polynomially many steps. And this can be done efficiently. Finally, this verification algorithm rejects if and only if a bad string is encountered in this random walk. So getting back to example, so if you start with 0, 0, 0, we could, let's say it has 2 edges, so it could move, for instance, to 1, 1, 0 because of the edge added because of P12. But then from 1, 1, 0, with some, let's say, rate half, you move to 1, 0, 1 because of the projector of the, because of the local term on qubits 2 and 3. But 1, 0, 1 is a bad string. So the May verification algorithm would reject in this case. And what Bredariol and Hall they show is that if this Hamiltonian has ground energy 0, so in other words, it's precession free, and x0 is indeed some string in the ground state of the Hamiltonian, then what they show is that the verifier never reaches a bad string. And this happens because the connected component of, they can show that the connected component of this string only contain good strings. So you can never have any path from this x0 in the ground state to a bad string. And then for soundness, they show that if the ground energy of this Hamiltonian is at least an inverse polynomial, then if a random walk is big enough, so but it's still polynomial, it should, this verification algorithm rejects with constant probability. And the idea why this holds is because somehow they can show that this the ground energy is related to the expansion in this implicit graph. And then if you give enough steps, then you should cover, you should pass by a bad string. When you consider, as we did, the very frustrated case, what we allow, like our main technical lemma is showing that if the Hamiltonian is very frustrated, then when you consider this graph, for every string that you pick in this graph, or every vertex that you pick, there is a bad string around very close to to it. So in particular, every string contains a bad string in a constant radius ball around it. And this gives directly showing that this uniform stochastic local Hamiltonian with constant promise gap is in NP, because the prover could give this initial string that's supposed to be in the ground state of the Hamiltonian, and the verifier just deterministically brute force search for a bad string on its neighborhood. And this can be done efficiently because the number of neighbors is polynomial, and the path that you want is constant size. And if it is a yes instance, as in the Braff interval case, with any path starting from the string in the ground state, we won't reach a bad string, so we never reject. But from our lemma, no matter what's the initial string sent by the prover, we know that there is a bad string on its neighborhood, so this brute force search must find it. And in this case, the verifier will reject with probability 1, or there's no probability involved. It will always reject. Any question? So I'll tell a bit more now about the structure of our proof. And it has two main steps. First, we show that there is a constant depth, what we call circuit of projectors, that achieves a state with a bad string. I'll explain it later what I mean by that. And we find such a constant depth circuit in an incremental way. So we show that either we have a state, we start with a state that contains a bad string, or we can find this set of non-overlapping projectors that will move us closer to having a state with a bad string. Then, assuming that constant size circuit, like a projection circuit exists that leads us to a bad string, then we can use the lightcon argument to retrieve a constant size path from it. So let me explain here in more details. So we know that the prover is supposed to send an initial string, x1, that's supposed to be in the ground state of this Hamiltonian. But we know that this Hamiltonian is highly frustrated. So there are two options. Either this string x1 is bad, in which case we are done, we have a bad string. Or what we can show is that we can find a lot of local terms that when you consider their projection of their ground space on projector of x1 onto its ground space, the projector onto its ground space, we have a string, we'll have a quantum state S2 that contains much more strings. So the support of the strings in S2 is exponentially bigger. Of course, I'm post-selecting on this projection. And then we can ask ourselves again, does S2 contain a bad string? If it contains a bad string, again, we are done, because that's what we want, a state with a bad string. But if it does not have, we can find another layer of projections that will lead us to some post-selected state S3 that contain, again, exponentially more strings than the state S2. And again, you can ask us again, does S3 contain a bad string? And you continue like that. And at every time, we add exponentially more strings to this state. So at some point, after constantly many steps, we have to have reached all possible strings, right? Because at some point, this exponential will get to 2 to the n. And when it gets 2 to the n, since we have the assumption that this Hamiltonian is highly frustrated, then there must be at least one bad string in this state. It has a lot of them, so it has at least one. So with these, we can show that these, like with these projections on the ground, with these non-overlapping projections, we can reach x1 to a state with a bad string in constantly many steps. And I'll wait 5 seconds for any question. Okay. So let me explain a bit more in details how this expansion works. So for that, we prove a lemma that we call a one-term expansion lemma. And in this lemma, we assume that you have some subset state, so a state that's the uniform superposition over some strings. And P being this k-local stochastic projector, meaning that a k-local projector of a projector onto the ground space of a k-local stochastic Hamiltonian. And we assume also that S does not contain any bad string for this projector on P. And okay, we also assume that P shrinks the state S, the subset state S, by at least 1 minus delta factor. So assuming all of these, having all of these assumptions, we show that when you project P, when you project S onto P, the number of strings in the support of this post-selected state is at least is related to the frustration that we had according to this projection. And the intuition of the proof is the following. So we know that this projection, so S does not lie in the +1 eigenspace of this projection. It's 1 minus delta far from it. But S does not contain any bad string for P. So this frustration must come from what we call missing strings. So strings that are neighbors from strings of S, but they're outside of it. And projecting onto P, we exactly add these missing strings, this delta over 2 as missing strings to this set PS. We can see this PS, the support of PS as a set. And then what we do is use this argument in parallel. So we have this non-overlapping expansion lemma, where we start again with a subset state, but instead of having just one projection, we have, let's say, L projectors. And every time we show that S project to P1 through Pi does not contain any bad string for Pi plus 1. And on top of that, we show that when you apply Pi plus 1 on the post-selected state of applying S on P1 up to Pi, this, again, it shrinks the state. So this post-selected state is far from being, it's 1 minus delta far from, it's delta far from being in the ground space of Pi plus 1. So assuming this, this subset state and these projectors, we're able to show that the support of S projected to P1 up to PL, the support of this of this state, it has at least 1 minus delta over 2 to the L more strings than S. So if L is linear in the number of terms, then it means that by finding such non-overlapping stochastic projectors, we can increase the number of strings in the state by an exponential factor. And the proof is very simple. We just apply the one-term expansion L times. And I won't get into details here, and then the only missing part is how to find these non-overlapping projectors. And this is, okay, when you know it is very simple. It took us a long time to find it, but it's just an adaptive argument, because we know that the Hamiltonian is very frustrated. So any state that you have should be highly, so for instance, if you have this post-selected state from S up to Pi, there must exist a Pi plus 1 that frustrates this state. And then you can just adaptively add this Pi plus 1 into the set. Okay, so this finishes the first part of the proof. And the second part of the proof, as I said, is moving from this constant depth projection circuit into a constant size path of in the graph. And one nice property of this circuit is that it has constant depth, as I said. But the problem is every layer could have polynomially many projections. So from this circuit, we cannot directly find a constant size path from X to a bad string. But we can do if we use the properties of badness. So here we have that a bad string is bad because it does not belong to the ground state of a specific local term. So let's say that the bad part of the string in this last state is marked here by red. So one good thing about this, the locality of the badness is that everything that does not influence what this part is cannot influence the badness of a string here. So in particular, if you can remove every projector on the last layer that does not touch the bits of these the bits here in red, they can be removed. And of course, here we remove the projector, so the state that we had here has changed, but this state must still contain a bad string there. And then we can repeat this argument over and over again. So we can remove from this second to last layer everything that does not influence what influences this red part. So in other words, you remove everything that is not in the light cone of this red part. So every time you remove from a layer everything that cannot influence the state on this red part. And since we assume that we have constant locality and constant degree, we have that when we remove everything that's not in this light cone, since this circuit has constant, the number of layers in the circuit is also constant, it means that the number of projectors that remain here, they're also constant. So in particular, if you consider the subgraph induced by these projections on the graph that we defined before, it has only a constant number of edges. And by the way that we chose these projections, it must be the case that in this subgraph, this initial string X is connected to a bad string on that small graph. Okay, and this allows us to retrieve from these constant many projectors a bad string, path from X to a bad string. And this finishes the idea of the second part of the proof. So we also have other so our main result is having this NP. We put in NP deciding stochastic local Hamiltonian has frustration 0 or a constant. But one thing that we can do is relax a little bit, and we don't need anymore that the stochastic local Hamiltonian has energy 0, but we can decide if it's tiny or constant. So that goes back a bit to the question by Andres. And so this gap amplification map, it does not need to preserve perfect completeness, but it can, but it could just slightly disturb it, and it will still be fine. A second and more recent thing is that we also realized that we can dequantize the problem. We don't like the result, like all the algorithms are classical, but we dequantize the problem. And we can see that the stochastic local Hamiltonians actually as an extension of constraint succession problems, but not for sets of strings. Then we call this problem a set CSP problem. And by translating the result of Gravinter-Hall and my result with Dorit in this language of set CSPs, we have that this gap amplification for this problem is also equivalent to MA equals NP. And I think this is a very nice contribution because we also, like this, classical people, they didn't, somehow they didn't know about the existence of this MA-complete problem because it's hidden in this quantum language, and somehow we were able to translate into some classical language. And let me finish with some open problems. So, of course, for me, the main open problem of our result is try to prove or disprove this stochastic PCP conjecture. And okay, some simpler questions towards this is trying to prove containment in P for smaller gaps, so not necessarily for quantum, for constant, but let's say inverse log or even bigger, inverse polylog. No, sorry, and inverse polylog is more, but anyway. And as I said, we have the case that we can distinguish the case for between tiny and large. And can you move further? Like you still have a constant gap, but now further from the initial point 0. Like for completeness, we could be, let's say, inverse polynomial, an arbitrary inverse polynomial, or even a constant. A second thing would be try to generalize our result to the non-uniform case. And there we have a part of our work would also follow for this non-uniform case when these rank 1 projectors are over arbitrary non-negative states. But the problem that we face is that then the frustration for the Hamiltonian does not come only from these bad strings, but it comes also from the inconsistency of amplitudes. And for example, if you have, let's assume just for example, when you have just a 1-qubit Hamiltonian and 2 terms on this 1-qubit Hamiltonian. And the first term is 1 minus epsilon 0, like the projector onto the ground space is on the rank 1 projector, 1 minus epsilon 0 plus epsilon 1. And the second term is epsilon 0 plus 1 minus epsilon 1. So by our definition, this Hamiltonian does not contain any bad string, but this Hamiltonian is highly frustrated because you can never be almost in 0 and almost in 1 at the same time. And Bredariol and Hall, they're able to deal with this, but as far as you see, this is not, they don't deal it in a local way. So we cannot reproduce the way that they deal with it in our case. And finally, the work of Bredariol and Hall, they use their containment in NA in a different setting, the setting of doing classical simulation of the adiabatic evolution of stochastic Hamiltonians. And I think it's an interesting open question, see if our result has some implication in this topic as well. And thank you for attention.
Thank you. Okay, so we have time for some questions. You can write them in the chat or raise your hand. Okay, there's a question in the chat. Yupan asks if this classical definition can be extended to frustrated cases, namely a combinatorial stochastic MA-complete problem. Stochastic MA-complete problem.
Yes, it can. Yeah, yes, it can. But then, and it would still be NA hard, and it would still be in NA. Like the point is, like stochastic local Hamiltonians can be translated, or at least uniform stochastic Hamiltonians can be easily translated into this language. Non-uniform ones could be also translated, but then you need to tweak a little bit this problem. But all of these results should easily translate.
And I was curious also about something. So what's your feeling? Like, do you think that there could be an approach to proving quantum PCP which does not prove the stochastic PCP?
The first question is, okay, there's also one point is that, for instance, we show that this gap version is in NP. So in our case, we're not very surprised because we believe NA to be equal to NP. So proving NP is somehow expected. Whereas if you prove that general quantum Hamiltonians in NP, this somehow disproves the quantum PCP conjecture because we believe that QMA is different of NP. So the first question is not clear, or at least not clear to me, that the quantum PCP conjecture should be true. So I think there are a lot of people in the audience that they maybe have more, like they know more about things to say, but for me the first question is not clear at all that a quantum PCP conjecture should hold.
Yeah, Alex, I have a question. So on your open problem side, you write disprove the stochastic PCP conjecture, but you proved that actually this this gap stochastic Hamiltonians problem is NP complete, right?
Yes.
Okay. So if you believe derandomization and believe that MA is equal to NP, then
you can only prove the stochastic PCP conjecture.
Okay.
Like if you assume KRG, like if you assume that MA equals NP, then you have a stochastic PCP conjecture.
Or put another way, if you disprove it, then that would also have some like circuit lower bounds, or it would disprove a circuit lower bound assumption or something.
Yeah, if you show that you cannot, the point is, if you show that this inverse polygap is not in NP, like this would be disproving this PCP conjecture. Then if you prove that this problem that is in MA is not in NP, then you show that MA is different of NP.
Right. Then that'd be huge. See. And yeah, maybe I'll follow up with sort of one more question. This is kind of more vague. So it seems to me like this, I don't really understand this this stochastic property. I mean, you define it formally, but it seems like is it a basis dependent definition?
Yeah, it is a basis dependent, and there are a lot of results by Joel Claassen, Marvian, Terhal. Okay, there are a lot of authors. I'll stop citing them. That trying to find if given a Hamiltonian, is there a basis that makes it stochastic? And yeah, here I assume that these Hamiltonians are given in this in the right basis.
I see.
Does it answer your question?
Well, I guess it was kind of an open-ended question. Like, so suppose someone walked up with a family of Hamiltonians that was stochastic in some basis, but you didn't know. Would you be able to say anything about that?
So far we don't know. So if you don't know the basis and you don't have any help telling you the basis to make it stochastic, then these procedures, they do not work, or at least not trivially. But what Barbara and Barbara is in the audience, if she wants to talk, I don't know. They show that some of these problems are in NP, and in this case, this could come with the proof, right? What's the basis that makes it stochastic?
Yeah, I can say something. We only made a start on this problem, and the only basis transformations we looked at are single qubit unitaries. If your Hamiltonian is not obviously stochastic, you say, I do apply single qubit unitaries to try to make it stochastic. And then in some cases, you can prove that actually single qubit Cliffords suffice, which is a discrete subset. And then you can ask, and then the problem is an MP because somebody could give you that Clifford if it exists. And then in some cases, we also proved that for some Hamiltonians, the problem of finding the unitaries is easy. But generically, we also show it's NP complete from other classes. But the thing is that these single qubit unitaries are only one choice, right? You could throw a constant depth circuit at it. You could throw a perturbation gadget at it. It's a lot of possible transformations. But I think Alex's results are indeed sort of independent of that, because in this case, you're given the Hamiltonian and the basis. It's just it's stochastic in the standard basis, the computational basis.
Amazing.
Can I ask a question, Alex, now that I'm sort of talking? So maybe I asked you this question before. So what about BPP and P? So because you can also take BPP, right, the Hamiltonian, and then you already know. Well, so say
So
some,
what we can show is, what we can show is that this, like if this map also, if you have extra properties for this map, then it exists. Then it shows that RP is equal to P. So one-sided randomized algorithms are equivalent to P. We cannot show for BPP. And this is because you don't know. So in some sense, like when you're talking about the random walk, we don't know what the warm start.
yeah,
Because,
I know.
because it's double, like, yeah, there are two-side errors. And RP, you can do it. So we don't know for BPP.
Thanks.
Thank you for coming.
Okay, good. If there are no more questions, and let's thank the speaker, let's thank Alex again. We can clap virtually in the chat.
Thanks, everyone.